Today we're on page 4 of the chapter 14 AP Chemistry Notes, and we're going to be finding the pH and the percent dissociation of a weak acid from knowing the Ka value. Whenever you have a weak acid, remember that this acid does not dissociate 100%. So whenever you have a weak acid or weak base, you're going to have to do an ice chart. So we'll start off by writing the dissociation of acetic acid, HC2H3O2. This is going to dissociate into H plus and acetate, C2H3O2 minus. All these are going to be aqueous. And you're going to be doing an ice chart for this. So we're going to write down ICE. And we know that we're starting with a 0.1 molar of the acetic acid. So this is what we're going to write in the initial right over here. And that means we have 0 of these to start. We have to shift to the right because there are zeros over there. We're going to follow stoichiometry with our change line. It's 1 to 1 to 1. And then we're going to find our equilibrium line right here. And now what we're going to do is we're going to use our Ka value, which was given to us. So remember that Ka is going to be the concentration of H plus times the concentration of C2H3O2 minus divided by the concentration of HC2H3O2. So we're going to put in our values. The Ka is 1.8 times 10 to the minus fifth. Our H plus is X, our acetate is X, and our acetic acid is 0.1 minus X. So now we're going to do our little trick where we're going to ignore our minus X because the Ka is very small. So remember, this number is very small. Negative fifth is very small, which tells you that this equilibrium favors the left side, which means it does not dissociate very much, which means this X that's going to come out of the dissociation is very, very small. And when you subtract a very small from 0.1, you essentially are going to have 0.1. You can't ignore this X and you can't ignore that X, but you could ignore it when it's subtracted or added to a number much larger than itself. Okay, when you do the math for this, you're going to find out that X is going to equal 0.0013. And of course, you have to check your 5% rule to make sure that this is okay. So and let me show you something with that as well. The percent dissociation is going to be the X over the original. So the X was the 0.0013 over the original, which is 0.10 times 100. And that equals a 1.3% dissociation, which is actually the same exact calculation as the 5% rule. So I'm going to write down that we passed the 5% rule. We're less than 5%. Okay, so that's finding the percent dissociation. Now we're going to find the pH. So the pH is equal to the negative log of the H plus concentration. The X is the H plus, so that's equal to the negative log of 0.0013. So that's going to equal a pH of 2.89. Now remember, I mentioned this before, that the pH, when you do sig figs, this has 2 sig figs. This only has 2 sig figs because the significant figures are always past the decimal. Numbers before the decimal in a pH do not count as sig figs because it's base 10. So this has 2 sig figs in the final answer. Now we're going to look at the problem below, and it's similar except we're starting with different information. So we're going to take the same acid, which is acetic acid. We're going to write down our equilibrium one more time. It's going to be the acetic acid, HC2H3O2, dissociating into H plus and C2H3O2 minus. Now this time they're telling us the Ka, and they're telling us the molarity, and we're trying to find the pH and the dissociation. It's the same exact problem actually, but now we're starting with a 1 molar So this is a 1 molar as opposed to the 0.1 molar. So we're going to do the exact same calculations over again. You could try to do this on your own and see if you can get it to work as I do it over here. You're going to make your ice chart, shift to the right, fill in your equilibrium numbers, set it equal to Ka, x squared over 1 minus x, oops, forgot to write minus x there, and then the Ka is 1.8 10 to the minus fifth. We're going to ignore this x again because the K is very small, and when you do that you're going to find out your x equals 0.0042 molar. So when we do our percent dissociation, it's x over original, so 0.0042 over 1 times 100. That's going to give you a 0.42% dissociation. And if we want to find the pH of this, pH is going to equal the negative log of the H plus, which was the 0.0042, and that's going to equal a 2.38, again with 2 sig figs, which are past the decimal. So let's compare these. You could see that the 1 molar, which is more concentrated than the 0.1 from above, this 1 molar, the more concentrated, has a lower pH, which makes sense. It has more acidity to it, so it's going to be a lower pH versus the 2.89. And next, we're going to see that the percent dissociation is different. And the percent dissociation of 0.42 is going to be a smaller percent dissociation. This is a smaller percent than the 1.3. So what's interesting is that the more concentrated you are as an acid, the lower your pH and the less your percent dissociation. There's less percent dissociation. And let's talk about why that is. Why that is. There's less percent dissociation because it breaks down less as a percentage than the top one. The more dilute an acid is, it's kind of like saying there's more water, okay? Because remember that these are all aqueous. AQ, AQ, AQ. At the top of the page, it was more dilute. So it's almost like you added more water in the first case. When you add more water, remember what happens? You shift towards the side with more aqueous. This side has 2 aqueous. This has only 1. So when you have 2 aqueous, there's more, and when there's more water, you're going to shift more to the right. So in the top example, it's like there's more water, so we shift to the right. Therefore, there is more percent than this one. However, the K, of course, will remain the same as 1.8 10 to the minus fifth.